I'll talk about diffusion, super-diffusion and non-local linear response in anomalous transport. And so this work is based on these two recent works. So let me start with a very basic setup of energy transfer. So if you attach two reservoirs of different temperatures across an extended system, then there will be energy current, flowing across the system, and associated to that there will be a temperature profile that gets developed across the system. And after a long time, the system reaches a stationary state, and there the current is related to the temperature profile by Fourier's law, which says that it's proportional to the temperature gradient, and the proportionality constant is a material property which we know as thermal conductivity. And it says that the value of the current scales with system size as 1 over system size L. And it also, one can easily see that for when the temperature difference is very small, the stationary state profile of the temperature profile is linear. And if you start from an arbitrary profile, it reaches to that profile obeying diffusion equation. However, there are many systems in lower dimensions, 1 dimension and 2 dimension, where the current in the stationary state is cannot be described by Fourier's law, which means that it doesn't scale with system size as 1 over L, scales as 1 over L to the power alpha, where alpha is between 0 and 1. And if we define the thermal conductivity in this way, it diverges with system size as L to power 1 minus alpha. And such a divergence has been observed accidentally in millimeter long nanotubes in the last decade. This is another signature of anomalous heat transfer, which is different from the previous setup. In this case, you consider an isolated system. Imagine you have a ring, and you prepare the system in thermal equilibrium, and then you place a small localized pulse in some place, in some point, and then observe the spreading of this pulse. So in diffusive systems, such spreading will be basically governed by diffusion. However, in systems which exhibits anomalous transport, this spreading is not diffusion. It actually has different spreading than square root T. These are other signatures. There are many other signatures. For example, the temperature flow is nonlinear even for smallest temperature difference, and it has some singular properties. The evolution of the temperature profile is not diffusive, and the total current autocorrelation function decays in equilibrium, decays as power law with time. And of course, there are other signatures that you can think of, like the exponent, how does it diverges and all, and of the temperature profiles. So the current status is that there is no general framework to study anomalous transport in generic systems, and that's why it's crucial to study specific model systems to understand different features of anomalous transport. And a fluctuating hydrodynamics theory has been quite successful in describing many of these features in wide class of systems, and this theory has got a significant development in the last decade, which is known as nonlinear fluctuating hydrodynamics theory. So I'll briefly describe this theory. Some of the features I've already mentioned by Herbert yesterday. So in this theory, you consider a lattice system, let's say, where each lattice side has some degrees of freedom, some position degree and momentum degree of freedom. And you consider a Hamiltonian in this form, which is written in some local energies, where you have a kinetic energy part and a potential energy part, and L is the stretch, which is this is the separation between two adjacent particles. So usually such a system has three conserved quantities: total stretch, total momentum, and energy. And corresponding to that, you will have local densities that if you do a coarse graining, will have continuity equations in this form. And under local equilibrium assumptions, you can express the currents in terms of the fields itself, and you get a hydrodynamic description. And on top of that, if you assume that the local thermal equilibrium is slightly deviated from the global equilibrium, then you can expand these currents into orders by order in the deviations from the global equilibrium. And if you expand the current in the first order, you get linear hydrodynamics theory, you get a matrix, recursive matrix, and that describes a ballistic propagation. So if you consider an excitation initially, that actually gets splits into 3 modes, one heat mode which doesn't move, and 2 sound modes which moves in opposite direction with equal speed. But if you add fluctuation and dissipation phrenologically to this theory obeying fluctuation dissipation, then these modes gets diffusive spreading. So in addition to the ballistic propagation, you get diffusive spreading, which is characterized by the square root is spreading. But if you add the second order term, the nonlinear term, then such diffusive scaling solutions may not be stable in many cases, and where you get ballistic propagation and the super diffusive scaling. And that's why you can get a super diffusive spreading of modes. So the nonlinear fluctuating hydrodynamics theory actually gives a description at a mesoscopic scale. So let me describe the different length scales from this picture. So at a microscopic scale, you have lattice, where you have particles, and you at this scale, at the mesoscopic scale, you actually take a coarse grain over many lattice sites, and which is valid over a length scale. So at this length scale, you actually take a zoomed out view of the particles, and these particles actually behave like fluids, but you still have fluctuations. You cannot ignore fluctuations, and you get a fluctuation and fluctuating field equations. Of course, you have to have a dissipation. And this is like a mesoscopic scale where you have a nonlinear fluctuating hydrodynamics, and that makes predictions at a much larger length scale, where you get super diffusion or Navier-Stokes type equation, heat diffusion equations. So you get a macroscopic aerodynamic description there. So as I said, that on macroscopic scale, nonlinear fluctuating hydrodynamics predicts super diffusive evolution. And the diffusion and the noise terms are added phenomenologically, and there has been attempts to derive those terms from a microscopic, starting from microscopic descriptions. For example, this paper by KG, Abhishek, Shinichi, and others. And this is another attempt that we have done some of with David and Julia and Asaf in 3-particle collision or ideal gas. But the presence of the diffusion term suggests that there should be a crossover from diffusive to super diffusive as you go from a smaller length, mesoscopic length scale to macroscopic length scale. And is it possible to see such crossover in such systems? And we have seen such crossover in this model, but I will describe similar crossover in other another model. Okay, so I'll talk about super diffusion in one-dimensional lattice systems, and I'll mainly talk about 2 models. One is this harmonic chain with momentum exchange. So you have a chain, and each particle has momenta and position, and they are connected by harmonic springs. So you have these dynamics, but and these barks are modeled by Ramanujan barks. And in addition to that, in the bulk, you have a stochastic noise which actually exchanges momenta of adjacent particles at some rate gamma. So these are like independent processes. Such actually dynamics conserves total stretch, total momentum, and total energy. It has 3 conserved quantities in this model. Another model that I would like to discuss is this model, which is called volume exchange model. So again, you consider a lattice where each lattice side has some variable, which is called a volume or displacement in the literature. And associated to each site, you have a energy. Here I am considering harmonic energy. And you have a deterministic part of the evolution, but is similar to the previous model. You have an exchange, bulk exchange noise, which actually exchanges these volume variables at rate gamma, and at each bond you have these exchange events which are independent processes. And this system conserves 2 quantities, the total volume and total energy. And this model was introduced by Cedric and Gabriel a few years back. And we have also have done some microscopic analysis of this model, but today I'll not do microscopic analysis. But I'll mainly, in the next, I'll mainly focus on this model, but later I'll present results, state the results for this model. Okay, so the corresponding to this conserved quantities, you can define, you can identify locally conserved quantities, which will have continuity equations, and these are kind of expressions for the current. So I just wanted to flash the expressions. But what we do, we first try to write down the Fokker-Planck equation for this model, and for the time being I have actually not taken the boundary part where you can attach baths, but when I'll present the model with the baths, I'll write down the Fokker-Planck operator from the baths. But these are the two parts, which is the first one is the Liouville part, and this is from the exchange part. And in this paper, Cedric and Gabriel actually they showed that when you have this, in the large system size limit, they call it infinite volume limit. In such a limit, this dynamics is ergodic in the sense that if there is an invariant state, that invariant state is actually mixture of Gibbs state, which I write in this form. And that state is actually characterized by two parameters, which is called temperature and pressure, or you can think of tension. So these are the two parameters which actually characterizes the invariant state, and they related to the average volume per particle and average energy in this way. So you can think of them as equations of state. So this is the setup of the problem. So you consider an initial state in which you prepare the system such that your average energy profile is like a slowly varying function which is slightly deviated from a global equilibrium, and similarly average volume profile or the displacement profile is also a slowly varying function and slightly deviated from an underlying global equilibrium profile. And you ask, as the system evolves, how do these profiles evolve? That is the kind of question that we want to ask and answer. So for that thing, we solve the Fokker-Planck equation. And as since I have, one can formally write down the solution in this form, that you have a local, slowly evolving local equilibrium picture. So you have a slowly evolving local equilibrium distribution plus a deviation. And since I have assumed that the deviations are always very small to the from the global equilibrium, I can think of this deviation to be very small. And this the slowly evolving local equilibrium picture is characterized by temperature profiles and tension profiles, pressure profiles, such that you have local equation of states. So the local volume and the local energy are related to the local temperature and the pressure in this way. Okay, so this is the solution that I take, and then see if try to find out what the temperature and the pressure profiles one needs to what equations, what evolutions they should satisfy, so that I always have these solutions for the Fokker-Planck equation. Okay, so this is the deviation. Deviation actually satisfies this exact equation, and you can write down formally the solution of this equation. And you can show that you can write it in this form, where this part you can still again write as in this form, where you have some current times some gradient of these fields, the average fields. And in the calculation we see a structure that these currents actually has this form, that you have the microscopic current minus a linear part that gets subtracted from this. That's what I am not going to the details of this calculation, but it will have this structure. Okay, so the strategy is we take average. That is the strategy that usually is followed. So you take average of these currents into this state, and then write down this, put it in the contained equation and get the equations for the average fields. So in the first step, if we just do this approximation, the distribution is just given by the local equilibrium distribution. And since we are assuming small deviations, I am considering only the linear deviations, so linear regime. So in this linear regime, you get local linearized hydrodynamics, which will give you a diffusion equation. This is actually similar to the hydrodynamics that these papers have written, but if you consider only the linearized version and neglect the diffusion and the noise terms in their equation, then you get this the same hydrodynamics. But if in the second step I consider the correction also, and then compute actually update the calculations of this average current, and you get a non-local linearized hydrodynamics, which in the continuum limit will provide me a super diffusive evolution for the temperature profile. So in particular, these are the equations that I get. H is the displacement field and E is the energy field. This is the pressure field and the temperature field. So I can write down the equations either in these two fields or in these two fields. So in the first step, I get diffusive equations, but in the second step, I get an extra correction, which is characterized by a non-local kernel. And that kernel, I find that it is given by integral of the current correlation in a global equilibrium state. And this is actually a nonlinear part of the microscopic current. So in the microscopic current, you can actually write down the linear part, linear in the deviations from the global equilibrium. So you have a linear part and the nonlinear part, and here actually the nonlinear part appears. And of course, for since we want to do hydrodynamics, so we want to do it in the large system size limit. So for finite size system, this actually doesn't make sense. I'll make it clear. So to make sense, you have to consider a combined limit of the system size going to infinity, and this upper limit going to infinite limit. I'll make it clear later. Yes. Okay. So, but the question is how to compute this quantity. So to compute this quantity, we let's consider an effective dynamics for the deviation of the volume field from the global equilibrium. So of course, this volume field actually has a drift part and the diffusion part from the exchange, but you also have a noise part because of the exchange Poissonian exchange events at the bonds. And since we are interested in the last limit, I actually approximated by some Brownian noise with appropriate strength. So I have a heuristic derivation for this equation, but I'm not showing it here, but I can have an explicit expression for the strength of the noise, depending on the global equilibrium values for the volume field and the energy field. Okay. So here I would like to make a remark is that this equation is actually similar to the fluctuating aerodynamic equation that you write in generic systems, but there you have this dissipation and noise terms, but you have nonlinear terms. For our model, for the volume field, you do not have a nonlinear term, but for the energy field, you have a nonlinear term. And for our model, we have only two conserved quantities. That's why you have two fields, and the corresponding normal modes are actually explicitly written in this form. So these are written explicitly in the. I actually forgot to put the reference by paper by Harvard and Gabriel. Okay, so this equation is very easy to solve, and it's a linear kind of Fokker-Planck type equation with a source term. So you can solve these equations, put it, and write down the solutions in terms of Green's function, and you can perform this. You can find that this microscopic kernel is actually given by this Bessel function explicitly. So we have these equations, or we have all the coefficients are explicitly known, but this is still not a hydrodynamic equation. So hydrodynamics equations are written in continuous functions. So we need to do continuous to write those equations in the continuous functions. So remember, we considered a slowly varying functions initially, and we expect that these functions actually will evolve also slowly. So that means they will still remain slowly varying over space as well as over time. So equivalently, you can write down that this temperature and the pressure fields are actually slowly varying functions, which are characterized by this macroscopic length scale and the time scales, which are measured in microscopic units. So if you do transformation like this, you can get continuum equations. But however, you have to choose appropriate scaling of these two scales to get sensible equations. So we have to choose a diffusive scaling for the pressure field, and you get diffusion equation for the pressure field. But for the temperature field, you have to choose the super-diffusive scaling, and if you do that, you get this equation. So this is the non-local kernel that you get, which is basically obtained from this scaling limit of this microscopic kernel, and you get a super-diffusive equation for the temperature field, but you have a diffusive correction, and epsilon c gives you a epsilon c inverse actually is expressed in terms of the microscopic parameter. and it gives you an explicit expression for the length scale. So below which you will observe diffusion, and above which you will observe super diffusion. I'll explain this, but before that I would like to mention that this equation was derived by Cedric in another paper, but from a different microscopic analysis, much more rigorous way. So here, let me explain this. So suppose you have an initially localized heat pulse and you observe the evolution. So initially it will start evolving. So this term will start dominate, and so the initial evolution will be basically diffusive as long as the spread is much smaller than this length scale. But when the spread is larger than this length scale, this term starts dominating, and then the spreading actually is given by the super diffusive scaling. So this is actually what we tried to see in the simulation, but it is difficult to see it in one system with one single parameter, such that you have some certain crossover length scale and you go from below to above. So it's actually very difficult. So what we do, we consider two sets of parameters, such that in one case you have very large this crossover length scale, and in one case it is very small. So that here the system says that we could study in the simulation, you see a diffusive scaling for the initial, you have an initially a very highly peaked temperature profile, and then actually spreads, and you see a diffusive spreading. Whereas in this case, the crossover length is very small, and you see a super diffusive scaling for the spreading. But such a crossover is actually is more easily demonstrated in open system study, where you actually attach reservoirs to the ends of the system, and those reservoirs are modeled by Lazarine reservoirs, and you follow the same procedure. You write down the Fokker-Planck equation, where you add this term into the Fokker-Planck operator. You do the same procedure, assuming that you have a local equilibrium state, which is slightly deviated from global equilibrium. You get the same equations and same form of the microscopic kernel, and you take a corresponding continuum limit. Here you have to take this corresponding scaling function like this, where epsilon is actually 1 over length of the system, and you get exactly same equation. Only difference is that it's actually over a finite domain, and you have to solve this equation with boundary conditions. An interesting fact is that even with the boundaries, you have the same position space representation of the kernel operator. They might have a different representation or spectral representation. It depends on the boundary condition, but the position representation is exactly the same. And in the steady state, the temperature profile satisfies this equation. And the energy current in the steady state, if you write down in terms of the functions, is given by this, where you have this piece from the super diffusive part, and this is from the diffusive part. So and of course, it looks like that this side is position dependent, and in the steady state, this should not be position dependent. It's actually not. You have to the temperature profile is such that it is actually not. So you can integrate both sides, and you find out the explicit expression for the currents. And in the leading order, you get an anomalous contribution, which is 1 over square root n, and then the diffusive correction. You can actually find out the constant C explicitly by finding the temperature profile. And this expression, you can write it in this form, and you can identify similar to the previous case and a length scale. And from this, you can see that when n is much smaller than nc, this current will scale with system size scale as 1 over n. But when n is larger than nc, it will scale as 1 over square root n. And that also we kind of see from the simulation. And once again, we choose 3 sets of parameters such that you get 3 choices of this crossover length scale. In this case, it is very large. Here it is very small. And in this case, you see that over the system set that you could study, the current scales as 1 over n, whereas in this case, it scales as 1 over square root n. And this is an intermediate set of parameters at which you get intermediate crossover scale. And here you see that it tries to decay as 1 over n, but then it crosses over. But it's very difficult to see from purely 1 over n to 1 over square root n. We have to go to very large NC, and you have to be able to find out currents for n larger than NC also. Okay, so I come back to the expression for the current, and this is the expression that we got. And if I use this scaling, this term is subdominant, I drop it. I can recast this equation in this form. You have a kernel like this, and I want to say that it actually generalizes the Fourier's law, in this sense that for the diffusive case, I can say that this is actually a delta function, so I get back the Fourier's law. But for anomalous case, it actually gets replaced by singular kernels. So for the volume exchange model, this kernel is this. For the momentum exchange model that I had presented earlier, one can show explicitly that is the kernel is given by this series of this kind of singular terms, and R is a parameter that actually has different values depending on the boundary conditions. Question is, how do we verify the forms of this kernel? They exist. There are indirect, of course, indirect verification. You can use this equation to find out the temperature profile and compare it with the simulation, and they actually match. So that's an indirect verification, but I want to do a direct verification. So that's what I do. I'll talk about in the next few slides. So remember, this microscopic kernel actually gave this kernel under the scaling limit, and the macroscopic kernel was related to the current correlation. And these current correlations are computed from the hydrodynamic evolution. But in the simulation, I cannot do this. I will measure only the microscopic currents, and I want to see whether I can identify this from the data of the microscopic current. That's what I want to do. So I define this microscopic current correlation and also define this integrated correlation. Then, if in this integrated correlation, if you take t going to infinity for fixed 10, you would expect that you will get a function of I and m, but it actually turns out that you can actually argue that it will be independent of I and m. It will be for all I and m, it will be a constant. So here you see that it doesn't depend on the location, but whereas in the hydrodynamic, you get a location dependent kernel. And how do we see that? So that means that is the question, that I want to observe this space dependent kernel from the correlations of the microscopic currents as measured in the numerical simulation. Okay. So so this is the correlation that I measure. So this is the current at time t, and this is the current at time 0. This is the mth bond, this is the ith bond, and I am plotting this. So I fix the mth bond to be the middle point, which is n by 2, and the ith bond I take 7 such bonds, alpha n by 16, alpha is 1 to 7, and I plot these curves for different I as a function of t. And you see that for each I there is a peak, and then there is a peak, and then it decays, and then it remains almost 0. You understand this from this following argument. The currents from this bond and that bond, they get maximally correlated when a sound mode starting from here reaches there. That's why when it gets maximally correlated, and that is where it is actually large. Just look at the red curve. So the maximum is reached at time I minus m. So all the maximum. So for different I, you see that the maximums are reached at this time. But whenever the sound modes are moving, they also get spread because of the diffusion. So the spreading at this time is given by this. So if I plot the corresponding integrations of this, it looks like this. So once again, focus on the red curve. It increases, and then it increases, and then after at this time, it doesn't increase further and it saturates. But you see that for all alpha, that means for all different I bonds, they saturate to the same value. That means that they don't depend on I and m, which is what I was trying to present here. So they don't depend. So the question is, where do we find the expression of the kernel? It turns out that if you take these values when the sound mode actually leaves this side, if you take the value of the integrated current at those points and plot them as function of z, which is this m by n, which is half, and u is I by n, which is alpha by 60. So that's the z. That is how the kernel actually appears, b minus u. If we plot it as a function of z, these values, then we expect that it should be of this form. And we see that it actually is 1/2 square root pi or 1/square root z in the increasing system size limit. So in the hydrodynamic limit, these values actually gives you this kernel. For this model also we verify. So say here I'm considering only the particular boundary condition, is fixed boundary condition, which is for this case this becomes explicitly this. So I would say that this in this case you have three conserved quantities, and you have two sound modes which are moving opposite direction. And once again I plot the current correlation as function of time, and you see that many peaks in positive direction and negative direction like this, and I'll explain that. So so suppose you have you start with a peak like this at the middle point, and then you are looking at the current correlation between this point and that point. There will be a peak when sound mode starting from here reaches here, then you get a peak like this. But this sound mode goes here and gets reflected, and when it gets reflected, it actually becomes from left moving to right moving, but it also changes phase. It becomes a negative. And because of that, this thing reaches here and you get another peak, but in the opposite direction. And it moves, but this peak also got reflected, and now it reaches here and you get another peak here. So you have first peak, second peak, and then you have a third peak like this, but in the opposite direction. And I would like to demonstrate that this term is associated to this event when basically a sound mode passes to this point without getting any reflection. This term appears after this the first reflection from the left, and this term appears after the second passing by event when this mode gets reflected from here, and yeah, so first reflection from the right. So so if I consider the time integrated function of this, you see this. So if you once again, if you focus on the red curve, you see that it actually increases. It increases, and after this, it tries to saturate. But when another peak, reflected peak, appears in the opposite direction, it decays and then again remains saturated. Then the next peak appears in the opposite direction, then again another decay like this. And then in the large limit, all of them actually saturate to the same value. Now I take the values after each when each at each state when a sound mode passes by at the end of this event, I take the values and plot and in terms of the scaling variable. So I see that if I take these values in the larger limit, they verify the first term. Now if I take these values after the second so that means the second passing by event, which is basically a sound mode which got reflected from the left and came back. If I take those values, then I should be able to verify this and this term, and that is what I actually get. If I plot them in terms of the scaling variable, I see that it actually follows this 1 over square root z minus 1 by 1 minus square root 1 minus z. So, but it's difficult to verify higher order terms in a finite size system because they also try to saturate. So you have to go to very large and to get sensible and reliable data from these collisions and this passing by events, this passing by events like this. So, so in conclusion, we have considered a local equilibrium picture, and considering such a picture, we have studied anomalous transport in a system with two conserved quantities, and we find super-diffusive evolution of local energy density across with a diffusive correction. And such diffusive correction allowed us to demonstrate a crossover from diffusive to anomalous transport. And we believe that if you consider a kind of a boundary wall problem with two different temperatures, one should actually solve this super-diffusive evolution equation. And then in the last part, we have provide a detailed extensive numerical simulation data to verify the detailed forms of the kernels that characterizes the non-local linear response relation, which I believe is generalizes the Fourier's law and the super-diffusive, and also characterizes super-diffusive evolution in the system. So once again, I will congratulate Deepak, and thank you all for listening.
So thanks, Anupam, for such a wonderful talk. So are there questions? Yes, Herbert.
So if I sort of understood correctly, I mean, you look at this response in terms of the correlations of the currents, right?
Yeah, the microscopic currents.
Yeah, that's right. I mean, now naively, you might have thought that you could also look at the correlations of the conserved fields, but are they somehow sort of easily related to the currents, or?
Yeah, they should be related by the some rules. Yeah,
Okay,
they should be
okay. So
related by
that's
some
what you're
rules.
saying.
But here the thing is, I have the boundaries, so I solve them with boundaries.
Yeah.
Some like purely Hamiltonian models like alternate mass gas, and so there are some special limits where you find like a diffusive phase for a long till some system size, and then there's supposed to be a crossover, right? So presumably it's the same mechanism as this.
I think so. I think so. I heard recently a talk by Lepre, and he was also talking about a similar crossover scale, and he have observed a diffusive kind of scaling, and then it crosses over, and that depends on the parameters of the
So, I
system.
mean, what would one need to do
But
in those kind of models to?
That I am not very sure. Actually, what I remember, he was trying to say that he was talking about the data in FQ chain, and he said that you have to take it very high temperature so that it actually very easily comes out from integrable limit, something like that. I am not very sure, but for this particular model, you have an explicit expression for the crossover, which is in terms of the parameters of the model. But for other case, I am not very sure. But definitely there will be such a crossover, which depends on the not only parameters, but also the initial state, at what temperature you have created. And here it doesn't depend on that, but I think it should also depend on, in nonlinear models, I think it will depend on that.
No more questions. Let's thank both the speakers of this session. So we return to this for the next session at 11:45.